Hi, in today's video we're going to talk about chips. Understanding chip formation is crucial to anyone who wishes to become a good machinist. A person who can recognize the different chip types and that understands how chips are formed, well, they can recognize the signs that indicate how to optimize their machining. We're going to be looking at three types of chips: continuous, discontinuous, and built-up or adherent chips. We're also going to look at cutting speeds, RPM, and feeds. So let's start by looking at the four phases of chip formation and the basic variables that affect that chip formation. Chip formation can be broken down into four steps: penetration, accumulation, formation, and separation. Let's look at each one of those steps in more detail. Penetration starts at the moment when the tool engages the workpiece. At this point, the tool is just trying to plow its way through the material, pushing it forward at the same time. This plowing motion applies huge constraints and forces onto the tool. At this point, the tool could fracture, especially if we were a little ambitious with the depth of our first cut. The second part of chip formation is accumulation. Now, it's to be expected that after penetration, which pushes material forward, that we're going to accumulate a certain amount of material in front of the tool. The accumulation of material is very important because it controls the temperature of the chip that we're going to produce. Heat is a very important part of chip formation, and we can control the amount of heat by controlling the amount of accumulation that we have in front of the tool. Accumulation is deformation, and to deform a piece of metal requires large amounts of force. This force and deformation translates into heat. The larger the accumulation, the more heat we're going to produce. The feed, the cutting speed, the depth of cut, and most certainly the angle of attack of the tool are the variables we can play with to control the amount of accumulation and thusly the amount of heat that we produce. If you're using high-speed steel cutting tools, you're going to want to form your chips at around 400 degrees Fahrenheit. If, however, you're using carbide cutting tools, 600, 650 Fahrenheit would be a better temperature. Now, there's probably some of you who are wondering by now, how am I going to measure the temperature of the chips that I'm producing? Well, you don't need to measure the temperature. You need to observe the temperature. In our video about heat treatment of steels, we saw that the color of steel changes depending on its temperature. For high-speed steel tools cutting into steel, well, we want a very light yellow or no discoloration whatsoever. However, if you're using carbide tools to cut steel, you're going to want a nice light or dark blue color. Now, the color of the chips and thusly the temperature of those chips is very important. As we know, steel's malleability and ductility increases with temperature. So it's important that we have our steel chips as hot as they can be to be able to make the steel flow up the face of the tool during the next phase, which is formation. Now, I mentioned that we want as much heat as we can get to form those chips, but not too much heat, because cutting by plastic deformation, producing chips, is a bit of a balancing trick. Not enough heat will impede the chip's capacity to slide up the face of the tool. Inversely, too much heat will make the chip either weld itself to the tool or make the tool melt. To be able to produce chips properly, you gotta walk that fine line between too hot and not hot enough. The next step is the chip formation. At this stage, the accumulation that is just ahead of the tool is starting to get pretty hot, and it's starting to act like a liquid. The metal accumulated in front of the tool has become very ductile and malleable, and it's being squished against the face of the tool. The material being crushed between the face of the tool and the accumulation really has nowhere to go. It's at this point, if all our variables are okay, that the chip will start to flow up the face of the cutting tool. We have at this point formed our chip. The final step in chip formation is separation. And separation of the chip is caused by a difference in temperature. Generally, metal chips have two surfaces. An inside surface, which is the surface that comes in contact with the tool, and the outside surface, which is the surface that doesn't contact the tool. The inside surface of the chip starts flowing from the very tip of the tool upwards along the face. It is the surface which has endured the largest deformation. The outer side of the chip comes from the surface of the part. It has been crumpled somewhat, but as a general rule has not endured much deformation. That means that the inside of the chip becomes very hot and that the outside of the chip stays relatively cool. Now, the heat on the inner side of the chip has a tendency to relax the stresses and strains caused by the deformation, whereas the outer side of the chip remains quite tense. It's that difference in surface tension from the inside to the outside of the chip which produces the curled shape that we recognize in most metallic chips. We can demonstrate this principle by using a strip of paper and a steel ruler. Now, this curve is very important because it's responsible for separating the chip from the tool. Now, it's very important to separate the chip from the tool as quickly as possible. The longer the chip stays in contact with the tool, the more heat will be transferred from the chip to the tool. Now, we want the tool to stay as cool as possible. So we want as much of the heat as possible to be taken away in the chip. So we're going to stop playing around with paper and go and take a look at what our three different types of chips look like.
I've gathered here a small selection of chips that are representative of our three basic chip types. In the upper left here, I have a selection of continuous chips. In the upper right, I have two discontinuous chips, and at the bottom here, I have a selection of built-up or adherent chips. Let's start by taking a closer look at the continuous chips. Continuous chips have a shiny interior surface and a matte exterior surface, and they have a long and spiraled shape. Even though they're all continuous chips, I have several different examples here. The first one at the top here is a chip produced on the lathe with a carbide cutting tool. The second one is a chip produced on a drill press using a high-speed steel drill. The third one is produced on a lathe using a high-speed steel tool, as is the fourth one here, just a little tighter. These chips to the left here are continuous chips, but they are segmented continuous chips because they were produced on a milling machine. Milling machines have discontinuous cutting action. These continuous chips are chips that have found the proper balance of all the variables that affect chip formation. It's this type of continuous chip that we want to obtain when we're cutting. The discontinuous chips are sometimes unavoidable. If we're machining cast iron, we will obtain only discontinuous chips. As we can see, these discontinuous chips are torn off more than formed, and they are the result of an excessive depth of cut and or an excessive amount of feed. These chips are to be avoided, since they are the result of an excessive amount of cutting force. They have a tendency to deform the part that we're machining and produce a very poor surface finish. The last group of chips, the ones down on the right side here, they are our built-up or adherent chips. They are the result of an excessive amount of heat. If our discontinuous chips were hard on the machining process because of the excessive force and the vibration that they produce, well, these built-up or adherent chips are bad for the machining process because of the excessive heat. They are integrally dull on both sides of the chip and have these long, filament-like, disformed chip shape. They don't have the characteristic curl that a normal chip would have. These built-up chips are the result of an excessive amount of cutting speed or a worn cutting tool. These types of chips should be avoided at all costs. If you persist with the cutting action that produces this type of chip, you'll most certainly melt the tip of your tool. You may also notice that when you produce built-up chips, the surface finish of your part is often grabby and dull, a little bit like Velcro. So there we have our three basic chip types. Continuous chips that we want to have, discontinuous chips that we want to avoid but sometimes have to put up with, and these adherent or built-up chips which are to be avoided at all costs. It's important to remember that chip production is the result of the variables we've chosen. And if we balance our variables properly, we should obtain that nice continuous chip.
Okay, so we've seen and are starting to understand how chips are formed. We now know that if we want to obtain a continuous chip, which is the type of chip that I want to produce, we're going to have to balance the amount of accumulation ahead of the tool with the material's fluidity, as well as the difference in temperature from the inside to the outside of the chip. Well, that's all well and fine, but we still don't know how to obtain that perfect chip. We're going to look at the four variables most often used to modify chip production. Those variables are speed, feed, depth of cut, and angle of the cutting surface of the tool. The first variable is cutting speed. The cutting speed varies depending on the type and alloy of metal that we're cutting. The cutting speed is presented as a distance that a tool has to travel in a straight line during a 1 minute period and obtain an optimal cut. An optimal cut can be defined as a cut that removes the maximum amount of material with the least tool wear. Imperial cutting speeds are given to us in feet per minute, whereas metric cutting speeds are provided in meters per minute. It's important to note that the cutting speeds provided in such books as the Machinery's Handbook, well, these cutting speeds represent a maximum. A maximum that we cannot attain unless all the other variables are perfectly adjusted. CS, or if you prefer cutting speeds, affect chip formation as follows. A cutting speed that is too low has a tendency to produce a discontinuous chip. Too high a cutting speed will tend to produce a built-up or adherent chip, and a proper cutting speed will obviously produce a continuous chip. We now have an idea of how cutting speeds affect the cutting action. But what about the tool angle? There are three separate ways of positioning a cutting surface to the work surface. And the first would be a positive cutting surface angle. And that is when the cutting surface of the tool describes an angle greater than 90 degrees from the surface being cut. These positive angled tools reduce the amount of accumulation in front of the tool, and thus they reduce the amount of heat within the chip. This reduction of heat within the chip is perfect for cutting soft materials, such as aluminum, which has a tendency to accumulate a little bit too much material in front of the tool and possibly welding itself to the tool. It is, however, important to note that positive angle cutting tools are the weakest tools because the quantity of material at the cutting edge is reduced. They are also thermically handicapped in that they can't dissipate heat as well as other tools, so they are to be avoided when machining hard or tough materials. To cut hard or tough materials, we want to use a negative cutting angle. A negative cutting surface is when the cutting surface of the tool describes an angle smaller than 90 degrees to the surface being cut. This negative cutting surface produces a larger accumulation ahead of the tool and a lot more heat within the chip. We've already seen that positive cutting angles are used for cutting soft materials. The reduced heat in those positive angle tools was a good thing because to cut soft materials you don't need to heat them up much more than what they already are. Too soft a material just plows. You can't force it up the face of the tool. So reducing was very good. Negative angle cutting tools, however, produce a lot of heat, so they're good for cutting hard materials. Happily, negative angle cutting tools have thick cutting edges that dissipate well the heat that they produce. It is, however, important to note that machining with negative angles requires a lot of force, and we need powerful machine tools to do it properly. Neutral angle cutting tools are a bit a mix of one and other of the tools we've just seen. They have the advantages and disadvantages of both. To show the difference that the cutting surface angle can have on chip production, I've sharpened three separate tools. The first tool on the left here has a negative cutting surface. The second tool, the one in the center, has a neutral cutting surface, and the one on the end over there at the right end has a positive cutting surface. So let's start by taking a cut with our positive cutting surface tool. It's important to note that all the other angles on these three cutting tools are very similar. All the cuts will be taken at 6/1000ths of an inch per rev as far as feed goes, and at an RPM of 500 revolutions per minute. The material that we're cutting is a C12L14, or if you prefer, a free machining steel. So, the tool is installed, my RPM, my feed, and my depth of cut are all set. My positive angle tool is ready to cut, so let's take our first cut. We're now going to use the tool with a neutral cutting surface. Now we can use the tool with a negative cutting surface. Okay, so now we have are three tools and the chips that they produced. The first cutting tool on the left side here is our negative surface cutting tool. And we can see that the chips are very tight, almost torn off, and that there is a slight discoloration that indicates that we were cutting very hot. Our second tool, the one in the center here, is our tool with a neutral cutting surface. We can see that the chip has a nice tight curl to it and that it is a continuous chip. The chip also has a nice color, very bright and shiny on the inside of the chip and very slightly dull on the outside. This is probably our best chip. And our last tool, the one at the very end here, was our tool with the positive cutting angle. We can see that the chips produced by that positive cutting angle have a very large curl and that they broke off in relatively short segments. They're also a lot duller than the chips produced by the neutral angled tool. This is an indication that we're probably cutting a little bit on the cold side. Surprisingly, these cutting angles are something that's almost instinctive in many of us, seen as it reflects something that we've been doing since we were very young. I often tell my beginners classes in machining that cutting metal is like cutting butter. And it really isn't a joke. We accumulate butter on our knife by plastic deformation. If the butter is particularly hard, we'll have a tendency to position our knife in a negative angle to accumulate a certain quantity. If the butter is very soft, we will naturally have a tendency to use a positive angle. And if the butter is of medium hardness, well, we'll tend to use a neutral cutting angle. So we can see that cutting butter and cutting metal is similar. Well, at least as far as cutting angles go. Well, this concludes the first part of this two-part video. In our second part, we're going to take a look at how depth of cut and feed affects chip formation. We're also going to look at RPM calculations and feed calculations. See you soon. Too high a cutting speed will tend to produce a an inherent lack of intelligence. Holy shit. Too high a cutting speed will tend to produce built up, for God's sake. Too high a cutting speed will tend to produce a built up or adherent chip.